And welcome back, my dear students. So far we have discussed up to lithium, and you know we are learning molecular orbital, and this is the 5th class, and today our target is to discuss the lithium onward molecules, and we will start today beryllium, and we will conclude our lecture up to discussing oxygen molecules. So let's continue our journey. Next molecule will be, I am erasing these, and remaining structure will remain same. And in your note you will draw another picture. I am not drawing it again and again. Okay, I am just erasing lithium and other things, okay, which will not be required in case of the discussion of the next molecule. And next molecule, of course, you can guess it will be, after lithium it will be beryllium. So the diatomic beryllium species is Be2. Now our target is to predict whether its existence is possible or not. So it has electronic configuration. B atom has electronic configuration 1s2, 2s2. So in 2s atomic orbital there occur 2 electrons. Now you just write, you just erase lithium atom from here, from here you write down, also erase this one and write down, and write down here, this is beryllium atom, this is beryllium atom. So in 1 2s orbital there occurs 2 electrons. You see, in one atom there occurs 2 electrons, and another beryllium atom there occurs also 2 electrons. So altogether in the beryllium 2 molecule we get 2 plus 2 is equal to 4 electrons. Now this 4 electron will of course reside, 2 will reside in the lowest energy at first, and next 2 will get then occupy the next higher level, that is next higher energy level molecular orbital, that is the sigma star 2s orbitals. And you see in all these cases different other principles which are valid for the fulfilling of filling up of the electronic configuration of the atomic orbitals, same here. For example, above principle, Pauli exclusion principle, Hund's rules of maximum multiplicity, all these are valid here. So we are following all those principles which are valid for the atomic orbital, and these are also valid for the molecular orbital, also for writing down the electronic configuration of the electrons in the molecular orbitals. So beryllium has now the electronic configuration, beryllium molecule, Be2 molecule has the electronic configuration sigma 2s2 and sigma star 2s2. So in the star orbital means it is anti-bonding. So in bonding 2 electrons occurs, in anti-bonding another 2 electron occurs. So 2 minus 2, bond order will be 2 minus 2, half of 2 minus 2 means half. So bond order is equal to, bond order of beryllium is, beryllium molecule Be2 molecule is 0. Bond order 0 means Be2 molecule does not exist as per molecular orbital theory. And next molecule, of course, what will be the next molecule? You can guess, it will be boron. And now erase all other things. At first you erase beryllium here, and then all these things in the right position. You should erase these things. Okay, you should erase these things. Okay, erase, and just wait for some second. Okay, let's continue the discussion. Okay, now our target is to discuss the formation of the Be2 molecules from the 2 boron atoms. Now one boron atom has the electronic configuration 1s2, 2s2, 2p1. Now one p orbital will be, there occurs 3 p orbitals, but in 3 p orbitals 1 p orbital will be occupied by the electrons. So here we have to consider 1 p electron. I am just writing in this way. So, 2 b atoms, in 1 b atom there will be 2s electron here, 2s electron here, 2s electron, okay, and additionally here will occur 2p electron, and there occurs 2 boron atoms. So, here there will occur 2p electrons, here there will occur another 2p electrons. So, in the molecule altogether, in boron molecules altogether there occurs how many number of the electrons? Total number of the electrons is 2 plus 2, that is 4 plus 2, 6 electron, altogether 6 electrons, and some are present in the 2s, sigma 2s, sigma star 2s, and some will present in the other molecular orbitals. Okay. Now, altogether what I mean to say, altogether there are 6 electrons, and our task is to put these 6 electrons in different molecular orbitals in B2 molecules. So, the electronic configuration of B2 molecules will be like this. So, at first the lowest energy, that is sigma 2s, will be occupied by 2 electron, and next higher energy of course is sigma star 2s, that will be occupied by another 2s. So, 2 to 4, and next level is the pi molecular orbital. You see, this is the pi molecular orbital, and this will be occupied by this. There occurs 2 pi orbitals, and which has the same energy, that is they are degenerate in nature. So, as per different principle which you have learned in your higher secondary classes, Pauli exclusion principle, Abba principle, Hund's rule, you know that in case of degenerate orbital, at first the orbital gets singly occupied, and then if the all orbitals are singly occupied, then only pairing is possible. So, here there occurs only remaining 2 electron, altogether there occurs, you see, altogether here there occurs 6 electrons, and 4 electrons have already been put in 2 sigma orbital, that is sigma 2s orbital and sigma star 2s. So, remaining electrons is 6 minus 4 is equal to 2. So, this 2 electron will be put in 2 molecular orbitals. In 2 molecular orbitals, so I am just writing, I am just drawing the electron here. So, these 2p will be filled, at first singly occupied, will be singly occupied, and another electrons are there, and this will go to the another 2p orbitals, and both will have the parallel spin. Remember, they will have the parallel spin in the same direction. We cannot write in this way. Okay. So, both will be in this, you have to write both will be in this direction. So, meaning, or you can write in this way also, that means they have the parallel spin. So, the electronic configuration is just like this. So, 2p, say this is 2py1, if you consider molecular axis along x axis. So, this is 2py, pi 2py, another pi molecular orbital will be 2pz, and this will be singly occupied. So, pi 2py1 and pi 2pz1. So, altogether 2 here 2 plus 2 plus 1 5 plus 1 6. So, 6 electrons will be accommodated in this way. Now, you try to calculate the bond order. So, how many electrons are present in the orbitals having asterisk sign? That is in the antibonding molecular orbital. It is only sigma star, that is the antibonding, and all other are bonding molecular orbitals. 2 are pi bonding, and remaining is the sigma bonding molecular orbital. So, number of the electrons, if you would like to calculate the bond order, so the formula is half number of the electrons in the bonding molecular orbital, that will be equal to the 4 minus 2 in the antibonding orbital, that is in the sigma star orbitals. So, ultimately it will be equal to 1. the bond order equal to 1. So B2 molecule, in B2 molecule we expect a single bond and its formation is possible, single bond, and its formation is possible as per the molecular orbital theory. And next you just go on increasing one by one electron. What will happen? The next electron will of course go in the next atom. If you consider the next atom, which will be the next atom, I am just erasing again and just again the next atom is after boron, it will be carbon, just erase those the things here, carbon. And what do we expect in case of carbon? The carbon has electronic configuration 1s2, 2s2, 2p2, you know from your higher secondary knowledge. So carbon, so we are considering now diatomic C2 species from 2 carbon atoms. Carbon has electronic configuration 1s2, 2s2, 2p2. So here additional 1 electron is present in the 2p orbitals. So 2p2 and remaining are same. So here it will be also 2p2. One is already there and I am writing the additional. So 2p2, and so all 2 additional electrons are coming here if you compare with that of the boron. So these 2 additional electrons you will have to put in the lower energy. They will actually occupy, their position will be here if in the pi 2p orbital. So here in this case pairing has occurred. So the electronic configuration is for the C2 is like this. You will try in your home all these things and it will be clearer to you. You will draw your own and will try to write the electronic configuration and it will be very clear to you in this way. So you write down in this way. So sigma 2s, sigma star 2s and pi, say it is 2py, and that will be completely filled, and pi 2p z, that will also be completely filled. In case of boron it was singly filled, and here since the number of the electron has increased, so total number of electron, you see how many number of the electron will be there. For one carbon atom, valence electron is 2 plus 2 is equal to 4. So if we consider 2 carbon atom, so 2 carbon atoms, so 4 plus 4, it will be 4 plus 4 is equal to 8. So here you see the number of the electron is also 8. 2 plus 2 plus 2 plus 2, it is 8. So in this way you can put all the electrons in different molecular orbital in case of the carbon molecules, and you just calculate the bond order. Bond order will be half of number of the electron in the bonding molecular orbital. You see except sigma star, all are bonding molecular orbital. So in the bonding molecular orbital, number of the electrons electron is 6 and minus it will be 2. So 6 minus 2 is equal to 4. So ultimately half into 4, so 2. So a double bond is indicated and its preparation is possible. Its preparation is possible at least as per molecular orbital theory. And next our target is the next molecule, that is the nitrogen. In case of nitrogen, I am erasing all these things. Okay, now it is very clear to you. In case of nitrogen, what will happen? In case of nitrogen, N2 molecule, the electronic configuration will be sigma 2s 2, sigma star 2s, pi 2py 2 and pi 2pz2 2pz2. So this is up to this, it is same as that of the carbon. Additionally, in nitrogen will have each nitrogen, you see in nitrogen nitrogen has electronic configuration 1s2, 2s2, 2p3. So the number of the valence electron, that is 2s and 2p electron, it is 5. So in case of n2, so 5 plus 5 is equal to 10. You have to accommodate 10 electrons. So up to the pi molecular orbitals, you have been able to, the pi bonding molecular orbitals, you have been able to accommodate 8 electrons. And next 2 electron will go to the next higher energy level molecular orbital, that is nothing but the sigma 2p. If you say this is 2py, 2pz pi, and this will obviously will be 2px, and so it will be W occupied, and electronic configuration will be just like this, in this way. So the bond order is, so except you see again sigma star 2s, all are bonding molecular orbitals. So the bond order will be equal to the half of number of the electron, 8 minus 2 is equal to, so half of 8 minus 2 is equal to 6, that is equal to 3. So in case of nitrogen, triple bond is indicated, and indeed the structure of the nitrogen molecule is N, triple bond N, you know it, I think. The next molecule, that is very interesting molecule, you see, and also this is the most important for our exam, since this is something exception. So that is the next molecule. Next our target molecule is to discuss the oxygen molecule, O2 molecule. Okay, so we will now discuss O2 molecule, and as we have mentioned earlier that in case of O2 molecule, the energy level diagram for the molecular orbitals are somewhat changed to some extent and will look like this. The sigma molecular orbital now, the sigma 2p molecular orbital now lower in energy than the 2 pi molecular orbitals. Okay, so the pictorial representation will be like this, and all other remaining same. So you now just join these things, say this is 2s, this is 2s, so this will be sigma 2s, this will be sigma star 2s, and now say this is sigma 2p, this will be pi, these two orbital will be pi 2p, and this will be pi star 2p, and this will be sigma star 2p. Okay, sigma star 2p. So this is the energy relative energy level diagram for the oxygen onwards diatomic species, homonuclear diatomic species. Okay, so how will be the electronic configuration? What is the electronic configuration of oxygen atom? It is 1s2, 2s2, 2p4. So in the valence shell, that is in the 2s and 2p, how many number of the electrons occurs? It is 2 plus 4 is equal to 6 electrons occur in the valence shell. So in each atom will contribute 6 electrons. So in O2 molecule, in the valence shell there occurs 6 plus 6 is equal to 12 electrons. Now these 12 electrons you have to put systematically, beginning from the lowest energy level, that is the sigma 2s will be filled at first. So this is sigma 2s, and next sigma star 2s, and next energy level, you see this is something new or new thing here, that is the sigma 2p orbital is lower in energy compared to that of the pi 2p. So next this sigma 2p will be filled, and next this pi 2p will be filled, and how many number of the electrons we have already put? This is 2 plus 2 is equal to 4, 4 plus 2 is equal to 6, 6 plus 2 is equal to 8, plus 6, 8 plus 2 is equal to 10, and total number of the electron is 12. So already we have up to this bonding pi 2p we have already put 10 electrons. So remaining 2 electrons we have to put in the degenerate pi star 2p level, in the degenerate pi star level. And as you have told before, since the level is degenerate, at first this pi level will be singly occupied. So it will be singly occupied, and so in the pi star level each orbital, in each orbital there will occur one electron. Okay. So the complete electronic configuration for the O2 molecule is sigma 2s2, sigma star 2s2, sigma 2p, sigma 2p 2, and pi. In pi orbital I am writing in this way now, pi say 2p, in 2p in bonding orbital altogether there occurs 4, 2 plus 2, 4 electrons. You may write in this way also, or you may write 2py2, 2pz2 in this way also. Okay, that's not not the problem. So up to this 10 electron we have accommodated, and the next, that is the pi star. See, this is pi star 2py, this is important, and another is pi star say 2pz, if we consider the px as the molecular axis. Now each these antibonding pi star orbital will have one electron. This is one, this is one, and this is, you must remember, this is very, very important. So the conclusion is, since there occurs unpaired electrons, you just remember, if there occurs unpaired electrons, so that will be that species will be paramagnetic. So oxygen is a paramagnetic species. This is very, very important, and frequently questions come like this: explain the paramagnetic behavior of oxygen in the light of molecular orbital theory. You have to draw the molecular orbital relative energy level diagram of the molecular orbital in this way, and then you have to actually prove that there occurs two unpaired electron in oxygen. Okay. So in pi star molecular orbitals there occur the unpaired electron, and that is why if there occur paired electron, that species will be diamagnetic, and if there occurs unpaired electron, that species will be paramagnetic. That is, that species will be attracted by the magnetic field. So oxygen is the paramagnetic species. That is very, very important. Now if you calculate the bond order of oxygen, what will be the bond order? So how many number of the electron in the bonding molecular orbital? You see, this is bonding molecular orbital sigma, this is sigma 2p, again bonding, pi 2p4 again bonding, and remaining are asterisk, means anti-bonding. So in the bonding there occurs 2 plus 4, so 8 electrons, and in the anti-bonding you see there occurs in the star orbitals 2 plus 1 plus 1, so 4. So 8 minus 4 is equal to 4, so half of 4 is equal to 2. So in oxygen a double bond is indicated, and indeed oxygen is the oxygen molecule there occurs a double bond, you know it. So this is the discussion of the molecular orbitals and from your syllabus point of view, and next day we will discuss some other things like how to draw different pi molecular orbitals of different species like ethylene, butadiene, etc., which are mentioned in the syllabus. Okay, and after that, thank you all for listening.